This animation demonstrates the continuity equation of ideal fluid flow, which states that the volumetric flow rate of an ideal fluid flowing through an enclosed space is constant.
Flippin' physics!
In other words, the cross-sectional area of the fluid at plane 1 times the speed of the fluid through plane 1 equals the cross-sectional area of the fluid at plane 2 times the speed of the fluid through plane 2. In other words, if the cross-sectional area of the plane decreases, the speed of the fluid flow increases. You can definitely see that in the highly idealized animation I made. However, this is also something you can easily demonstrate with a standard garden hose. In fact, I bet you already unknowingly have. If you have a hose with water flowing out of it, you can put your thumb over the end of the hose to decrease the cross-sectional area and therefore increase the velocity of the water flowing through the end of the hose. And you can see that the water flowing out of the hose where I used my thumb to decrease the cross-sectional area at the end of the hose is moving faster because that water has a larger displacement in the x direction in projectile motion. Clearly, once the fluid has left the garden hose, the water is no longer constrained to the garden hose and the continuity of equation of ideal fluid flow is no longer valid. However, it is valid in the garden hose all the way up to and through the plane at the end of the hose where the water enters into projectile motion. I definitely suggest trying this at home.